Blitzer 5.2 sum and difference formulas. So we start out with these sum and difference formulas for cosines and sines. So like something that I notice is where I have the two cosine of adding two angles or subtracting two angles. When you look at the formulas, it's cosine first and then sine. And then the one with a plus has a minus, one with a minus has a plus. When we look at sine, the signs match. So they're plus, they're minus, and then these ones are sine and then cosine, cosine and then sine. So just some different stuff about how those work. There's sum and difference formulas for tangents also. So with the tangent formula, we notice that the sign and the numerator is the same and the denominator is different. So these are more formulas to memorize. Each day in class, unfortunately, I'm going to be giving you more stuff to memorize. So for example 1, they want us to figure out the exact value of cosine 15. So exact value tells us to not use a calculator. And I know that when I work with angles, I can do 30s and 60s and 90s and 45s. I can do multiples of those, but I don't have anything as small as 15. So how am I going to find the exact value when I don't have a fancy special triangle with a 15-degree angle? So that's where these sum and difference formulas work. So remember that our good angles that we want to work with are like 30 and 45 and 60. And we want to think, how could I get a 15-degree out of this? Well, I could do 60 minus 45. I could do 45 minus 30, either of those ways. And they'll actually both work. They'll both give you the same answer. So I'm going to start out my problem here by writing cosine of 15 degrees because that's what I'm doing. And then I'm going to make it cosine of 45 degrees minus 30 degrees. And again, you could do 60 minus 45, you get the same answer. So then if I'm going to use that formula, remember with cosine, when it's minus, it's a plus, and we have cosines first and then sine second. So it's going to be cosine 45 degrees, cosine 30 degrees, and then plus, and then sine 45 degrees, sine 30 degrees. So all I'm doing is I'm using that formula above for the cosine of the difference of two angles. And now I'm going to have to draw some triangles. So my 45-degree triangle, I'm going to draw over here. And we're going to talk about how this triangle, maybe we need to update it a little bit for 45 degrees. And then I also need to have a 30-degree triangle. So across from the 30 is the 1. So cosine 45 degrees. Let's see. So cosine of 45 degrees would be 1 over square root of 2 times cosine 30. That's going to be square root of 3 over 2. And then plus sine of 45, 1 over square root of 2. Sine of 30 would be 1/2. So I've got to rationalize these right away in order to be able to do anything with this. Eventually, I'm going to have to rationalize. Sooner is probably better. So square root of 2 over 2, square root of 3 over 2. And then let's see. When I multiply now, I have square root of 6 over 4 plus, oh, you know what? I did not rationalize over here. Square root of 2 over, let's grab an eraser really fast. Over 2. Okay, so square root of 2 over 4, common denominator, which is excellent. So when I add them, it's just going to be square root of 6 plus square root of 2 all over 4. And I believe if you do 60 minus 45, the numerator ends up being switched around, but it's just the same exact thing. So looking at how we're always having to rationalize and thinking about how cosine is my x over my r, that means that a different triangle I could use instead of 1, 1 square root of 2 would be if my x and my y sides were both square root of 2 and then my radius was 2. And that might be a little bit easier to work with, especially when we're doing all these crazy fractions, so that I'm not always having to then go ahead and rationalize. So that's just something to think about. And if this is just ingrained in your head and you can't switch, that's fine. But I think it might make sense to think about how this is my x and this is my r. So I've got my x side, my r side. It's just like an already rationalized version when we're doing sine and cosine. So for example 2, let's see, I've got sine 80 degrees, cosine 20 degrees. Okay, so this is definitely one of those sine ones, right? Cosine 80 degrees, sine 20 degrees. So we know with the sines, the angles match. I guess I better write my original problem. So sine 80 degrees, cosine 20 degrees. So it's going to be something with 80 and 20 minus cosine 80 degrees, sine 20 degrees. So this is basically this is basically the difference of two angles for sine, isn't it? So this is like the expanded out version. So what I want to do is I want to change this back because I can't do anything with 80 and 20, but there is a minus sign here, and I know what 80 minus 20 is. So this is really the sine of 80 degrees minus 20 degrees. So just to review, this is what I'm doing right here, right? Sine alpha cosine beta minus cosine alpha sine beta. That's what we're doing. Oops, somehow I just totally blew that up and did not mean to. There we go, that looks better. So this is sine of 60 degrees. And then I would need to draw 60. So 30 is up here, 1 would be down here, square root of 3, 2. And so my sine is going to be y over r, or square root of 3 over 2. All right, so for our third example, we're going to look at tangent. And that tangent formula was a little bit trickier, and I've got the 7 pi over 12. So I know that the easy angles to work with are 30 and 60 and 45, but I don't know what that would be in radians. So let's worry about that. So let's see, 30 degrees would be pi over 6 radians. That's going to be 30 degrees. If I'm looking at 45 degrees, that's pi over 4. And if I'm looking at 60 degrees, that's going to be pi over 3. The issue here is I've got over 12. So I'm going to change these all into 12ths to kind of figure out how I could add these angles together and get that. So pi over 6 is really 2 pi over 12. Pi over 4 is really 3 pi over 12. And pi over 3 is really 4 pi over 12. So it looks like I could break this 7 pi over 12 into two angles, 3 pi over 12 and 4 pi over 12. And then that would fix this for me. 3 and 4 would make that 7 pi. So let's go ahead and get started. So tangent of 7 pi over 12 is tangent of 3 pi over 12 plus 4 pi over 12. And because we're in radians, we're staying with radians. And so then this is going to be tangent of, when I reduce pi over 4 plus pi over 3. Okay. And then I need to go ahead and write out that sum of two angles for tangent. I need to go ahead and write that down. So this is going to be tangent pi over 4 plus tangent pi over 3 all over 1 minus tangent pi over 4 times tangent pi over 3. So now, of course, I'm going to have to draw pi over 4 or 45 and pi over 3 and go through and figure those out. So let's see, pi over 4. And I'm going to use my rationalized version again. So square root of 2, square root of 2, 2. And then let's see for pi over 3. So the pi over 3 is the 60 that's across from the square root of 3. 1, 2. These aren't always going to be in the first quadrant, but the angles that we're working with on this, on the notes, are pretty small. So let's see, tangent of pi over 4, that's going to be square root of 2 over square root of 2. So that's just going to be a 1. So I didn't even need that fancy triangle. Tangent of pi over 3, so that's going to be square root of 3 over 1. So that's just plus a square root of 3. And then in my denominator, 1 minus, well, tangent pi over 4 is just a 1. Tangent pi over 3 is a square root of 3. Okay, so then what we really have is 1 plus the square root of 3 over 1 minus the square root of 3. But then I have to rationalize. So I am going to multiply this by 1 minus root 3 over 1 minus root 3. And in the numerator, 1 plus over 1 plus, right? Because I need the minus and the plus in the denominator. So in the numerator, when I multiply this out, it's squared. So I'm going to have, let's see, 1 times 1 is 1. In my middle term, 1 times square root of 3 doubled would be 2 square roots of 3. And then square root of 3 times square root of 3 would be the square root of 9. In my denominator, I know I'll just have 1 squared is 1 minus square root of 3 squared is just 3. So a little bit more work to do here. So I'm going to have to kind of go over. So 1 plus 2 square roots of 3 plus 3 all over negative 2. Let's see, 3 and 1 would be 4 plus 2 square roots of 3 divided by negative 2. And then I want to divide that through. So negative 2 minus square root of 3. So I think the tricky part on a lot of these is actually just going to be manipulating the fractions and the roots and not even actually the math. So this last one's kind of interesting. We're going to verify the cosine of negative theta equals cosine theta. So that's one of our even odd identities from yesterday. So we're going to think of cosine. Let's go ahead and write it down. Cosine of negative theta equals cosine theta. And then let's think of negative theta as cosine of 0 minus theta. Remember, we're only working on one side. So using my my properties that I just wrote down, those formulas, I have the difference of two angles. I have a 0 and I have a theta, and we don't know what theta is, but that's okay. With cosine, those are the ones that start with cosine and end with sine. And if there's a minus, there's a plus. So we're going to have cosine 0, cosine theta, and then plus, and then we've got sine 0, sine theta. And I could put degrees or I could not put degrees because 0 degrees or 0 radians, either way. My equal signs don't line up. I just did not have enough space, but that's okay. So now let's look at 0. So on the unit circle, here's 0. And at 0, I've got that ordered pair 1, 0. And so my x is 1, my y is 0, and my r is 1. So let's think about what's going on here. So my cosine on the unit circle is like x. So that's going to be 1 times cosine theta. And then plus sine of 0 would be my y at 0. Because I'm on the unit circle, it's just y by itself. So that's 0 times sine theta. So 0 times sine theta is just gone. And then 1 times cosine theta is just cosine theta. So we have proved this identity. We have verified the identity that it actually works. So I thought that was kind of a cool application as well. So I will do my best to get the 5.3 notes up soon. It could be that you finish the 5.2 homework early and you want to look at power reducing before Thursday. And that is perfectly acceptable if you think that you need to move ahead and you're all caught up. So have a great day, class.